Okay, so today we will go inside the theory of multilinear p alternating forms, the theory of differential forms over a manifold, and also the definition of actually an operator of exterior derivation for a given differentiable manifold. So let's see what are the p multilinear alternating functions over a vector space V. Let V be a vector space of dimension n, a map V times V p times into the reals. Let's call this map omega, is a p linear alternating form if for each v1 vp belonging to V, omega of, let's say, dot 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 vi dot 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 vj dot 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 is equal to minus omega of dot 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 vj dot 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 vi dot 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 closed parenthesis. The set of all p forms over vector space V will be denoted with lambda p of V star. And we set lambda 0, and obviously lambda 0 of V star is actually the field of the reals, while if p is bigger than the dimension of the space vector space V, then lambda p of V is equal to only to the 0 vector. Now now a p index is a set of indices a1 a p where ik goes from 1 to n, and it's also increasing p index in case i1 is less than i2 less than blah 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 less than ip. So an increasing p index is defined. Now if a1 an is a basis for V, we can define the dual basis a1 an with the indexes on the top, such that ai aj is equal to delta aj. Now the number of p indices, increasing p indices, is actually equal to the factorial n over p. So if we can define, so given a p index capital I, we define an element of lambda pv as e to capital I, which acts on vectors v1 vp as the determinant of ai vj. Now the set, if a1 an is a basis for V, then the set of ei capital I is a basis for the p forms over V. So the dimension of p forms over B is actually equal to the factorial n over p. Now, setting lambda 0, as we already said, lambda 0 of V equal to the reals, we can define lambda star of V star equal to the direct sum of over P from 1 to n of lambda PV star. Those are actually the set of the complete set of all forms we can define over the space V. So an element of lambda star V star can be written as the sum of omega 1, omega 0, omega 1, plus omega 0 plus omega 1 plus omega 2 plus blah 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 omega p, omega n, where omega k belongs to lambda k of v star, and an element of the form 0 blah blah point plus 0 plus blah 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 plus omega plus 0 plus blah 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 plus 0, where omega is when omega is in lambda k of v, where these type of elements are called pure forms, and omega will be called pure forms of degree k. Now let p and q be two integers such that p plus q is less than n. We define with the GPQ the set of all permutation of p plus q symbols, permutation sigma, such that sigma 1 is less than sigma 2 less than sigma p, and at the same time sigma of p plus 1 is less than sigma p plus 1 is less than sigma p plus 2 less blah 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 less than sigma p plus q. Now, if alpha is a p form over v and q is a q form over v, we can define, given a set v1, vp plus q of vectors of v, we can define the product of these two by writing alpha wedge product of beta v1 vp plus q equal actually to the sum over sigma belonging to GPQ of alpha v1 vp alpha v sigma 1 v sigma p beta of v sigma p plus 1 v sigma of p plus q. So we have this definition. Obviously to multiplied by minus 1 to the power of sigma. If p is equal to 0, then alpha wedge product beta will be just the product of the scalar alpha with the form beta. We have got a theorem. If alpha is a p form and beta is a q form, then alpha product beta is a p plus q form. By extending with linearity, the wedge product becomes actually a map from lambda star v times lambda star v into lambda star v by extending by linearity, and the couple lambda star v with the wedge product becomes an associative algebra. Furthermore, if I is if a1 an is a basis for v, and a1 an is a basis for the dual of v, and capital I is a p index, increasing p index, then we have that ei is actually equal to e1 wedge product e2 wedge product blah 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 wedge product eip. Furthermore, alpha wedge product b is equal to minus 1 to the degree of alpha degree of beta wedge product alpha. The rule for the basis is actually that the ai wedge product ej is equal to minus ej wedge product ei, and ei wedge product ei is equal to 0. We can define another operation which is called the interior product. So if we pick up a v in a vector of the vector space and a p form alpha, then the interior product of v with alpha is a p minus 1 form, defined in the following way. If v1 v p minus 1 are p minus 1 vectors, then iv of alpha applied to v1 vp minus 1 is actually equal to alpha v v1 vp minus 1. This is the interior property. This defines an operation from extending by linearity, an operation from lambda star v star into lambda star v star. And also EV or lambda p v star is contained in lambda p minus 1 v star. If alpha and beta are pure forms, then EV of alpha wedge product beta is equal to EV alpha wedge product beta plus minus 1 to the degree of alpha wedge product EV of beta. Furthermore, if W and V are two vector spaces and L is a map from W into V, then for each p-form defined over V, we can associate a p-form defined over W by means of the following. L star of alpha, if alpha is a p-form over V, when applied to vectors W1, WP belonging to W, we obtain that this is actually equal to alpha LW1 LWP. Now we can construct out of the p-forms defined over the tangent space at a point P of a given differentiable manifold, we can define a fiber bundle. How can we do this? Now, obviously, we have for each point P of M, we have TPM, the tangent space to the point P. We have the dual T star PM, and we can obviously construct the lambda P of T star PM. Now, the fiber bundle we are going to analyze is the union with P belonging to M of lambda P T star PM. There's a natural projection pi which maps lambda P of PM of T star PM into P. Natural projection. How can we construct, for example, an atlas for this fiber bundle? Is very easy. Consider a point P in M and an open chart U phi of P covering P. Set U prime equal phi of U. Then, for example, if X is equal to phi of P, then a basis for T x of U prime is given by the partial derivatives. And there's also a dual basis, the x1, the xp, such that the xi derivative with respect to xj is equal to delta ij. But if I is a multi-index, then dx to capital I is equal to dxi1 wedge product dxip. And by running I over the set of all increasing p indices, which in number are equal to m over p factorial, which we will call now capital M, m over p we will call capital M. We have that form alpha of lambda, let's say lambda p tx of u prime can be written the sum over all these p indices of alpha I dx capital I. So to each form we can associate a vector which is actually equal to x and alpha 1 alpha capital M, which is an element belongs actually to u prime times Rm. So we can in this way construct a map capital phi. This capital phi is a map from pi to the minus 1 of u into u prime times r to the power of m, and is defined as follows. Phi is actually equal to phi, capital Phi is equal to phi differential of phi to the minus 1 dual of this. And the map phi is such that the following diagram commutes. Pi to the minus 1 of u is mapped by capital Phi into u prime times r to the power of m. Pi to the minus 1 of u is mapped by pi into u. U is mapped by phi into u prime. U prime times r to the power of m, capital M, is mapped by the projection of the first component into u prime. So this diagram commutes. Now, for example, if we have two charts, u phi and v psi, which are neighbors which intersect one to each other, and we have a point P inside the intersection u intersecting v, then we can obviously define capital Phi and capital Psi, where capital Phi goes from pi to the minus 1 of u into u prime times r to the power of capital M. Capital Psi goes from pi to the minus 1 of v into v prime times r to the power of capital M. And we can construct psi composite phi to the minus 1. Capital Psi composite capital Phi to the minus 1. And this map is actually goes from u prime intersecting v prime times r to the power of capital M into u prime intersecting v prime times r to the power of capital M. We can show one can show actually that those are differentiable functions. So the fiber bundle lambda star of Tm star is a fiber bundle which is a differentiable manifold, and all the smooth sections of this fiber bundle are called p-differential forms. The set of p-differential forms will be indicated with lambda p of m. The p-differential forms of m. Natural definition. Now, if alpha is a p-differential form and beta is a q-differential form, alpha wedge product beta is a p plus q differential form. Furthermore, if alpha is a p-differential form and x1, xp are smooth fields, the map x into alpha x, x1 of x, xp of x is a smooth map defined over M. This means that any differential p form will define a map which is actually a map from key infinity, key m times key m p times into c infinity. This is the real valued smooth function defined over M. Okay. Now let T be a map of the type key m times key m p times with values in C infinity, such that is C infinity linear and is also alternating or antisymmetric. Then for each x1 xp belonging to key p, there exists then there exists a p form, differential form alpha, such that t of x1 xp is equal to alpha x1 xp for each x1 xp belonging to the set of smooth vector fields defined over M. Furthermore, if F is a C infinity map from a differentiable manifold M into a second differentiable manifold capital N, then we can build the so-called pullback of a differential form. So if alpha is a differential form over M, differential P form over N, then f star of alpha is a differential form defined over M, and for each x1, xp belonging to key M, one defines f star of alpha x1 xp equal to alpha differential of f computed in x1 dot 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 differential of f computed on xp. And this new form f star alpha is called the pullback of alpha. Now we are going to introduce the exterior derivation of a given manifold M. Now one can set lambda star M equal to the sum over P from 1 to M of lambda P M. Okay. There's a natural map called the exterior differential, exterior derivation D, which goes from lambda 0 into lambda 1 over M, and is defined as follows. If f is the germ of a smooth function defined in a neighborhood of a given point P of M, and V is a vector of the tangent space to the manifold M in the point P, then dfp of V is equal to VFP. So we have the action of the derivation V over the germ of the smooth function f. This means that, and obviously dfp of V is df of P is actually an element of the dual space of the tangent space, so it's an element of T star Pm. Now we want to extend the exterior derivation to the whole lambda star M. How can we do this? A map D, an operator D from lambda star M into lambda star M is an operator of exterior derivation if it is R linear, if D of lambda Pm is contained in lambda P plus 1 M, if for f belonging to C infinity function defined over M, df is a one differential form defined as we have already said. If f is a smooth function defined over M, then d square f is equal to 0, and 5. If alpha and beta are two differential forms, then the d of alpha wedge product beta is equal to d alpha wedge product beta plus minus 1 to the degree of alpha wedge product d of beta. Now, if U is an open set of the manifold M such that the form alpha is vanishing on U, then d of alpha is equal to 0. Furthermore, in each point P of the manifold M, there exists an open neighborhood U of P such that each form alpha can be written in this neighborhood as the sum of forms of the type, let's assume that alpha is a P form, it can be written as sum of P forms of the type F, df1, dfp, where f, f1, fp are C infinity function defined over M. Any operator of of exterior derivation defined over the whole manifold M induces an operator of exterior derivation over any open neighborhood, open set U of the manifold M, and we will call this du. Now suppose that U is an open set of Rm. Then the differential of a smooth function defined over U, so a function of C infinity U, is actually quite easy to write down. If, for example, alpha is a P form, so is a lambda P of U, and is written as f of di, where I, capital I, is an increasing P index, then we have the differential of alpha can be written as the differential of f wedge product dx to capital I. In this way, by extending by linearity, we obtain a derivation, an operator of exterior derivation over lambda star of U. Okay. On every differentiable manifold, there exists an unique operator of exterior derivation. This is a theorem. Furthermore, if alpha is an element of lambda 1 M and x and y are smooth fields over M, then the differential of alpha applied to x and y is equal to x alpha of y minus y alpha of x minus alpha applied to the commutator of x and y. And to conclude, if f is a map from M to N, then the differential of f star of alpha being an element of lambda star n, the differential of f star alpha is equal to f star differential of alpha. And this concludes everything.